So thank you for coming tonight. Actually, the plan of this talk today will not be directly related to the paper, like in the first. So what I'm planning to do is that just to give you kind of an overview about, like the reality or the context that led to this paper, and that might be like the first half of the talk, and the second half I'll like go through the paper. And the goal of that, the objective really of this talk, is not just like to think about because this paper it's different from regular papers that I think you've seen here. And the goal of this talk is to start thinking about the machine learning in general in a different way. So like I'll consider this talk as successful if you ended up with new questions, or we start thinking that there are new directions for research that you could pursue. Now, to be honest, like in the beginning, I'll speak a little bit about the current reality, like of machine learning research. And it seemed that, we have, like for machine learning, we have different groups that are working on solving this problem, the problem of assigning learning, or embedding machines with learning. And that problem didn't start off today. Like there's a kind of a historical roots for this problem that led to the situation, like of this. So in order to understand clearly the context of this paper, like I need to give you like a little bit of history about, about the scene of machine learning. So really one of the problems, like the deep learning, one of the main, like groups right now, this is like, one of the major groups in trying to solve machine learning is based on neural networks. Now the thing here is that concept, that group is really an offshoot of a psychology. So like there's this group in psychology called Connectionism. This is a school of psychology that was looking at the mind in a specific way. And that's really what led to neural networks. So the first, what I'd like to do is that in the yeah. Okay. Sorry. So in the first few minutes, what I'd like to do is that to give like a kind of a brief overview about how we ended up with deep learning as of today. Now, again, like usually when we speak of that time, like of that topic, like topic of history, we have to start with the beginning, with the starting point, and that's kind of a controversial issue. So I don't want to go too deep in the history. So I'll start from the 19th century. That's about like 150 years ago. Now, psychology at that time wasn't really like a kind of a proper science as it's understood today. It was really part of a philosophy. And again, like history of philosophy is a major thing that we're not going to in this thing. But like just to give you like a kind of an example of that time, there was this philosopher called Herbert Spencer. He wrote like a lot in philosophy in general, and he had like kind of a major writing in philosophy in which like he has a volume named The Principle of Psychology. And if you look at that, like at that book, it was like published around like mid 1800s, mid 19th century. You see that the first chapter in that book is called The Data of Psychology. Like now, if you would look at that chapter from today's understanding, you say like, so maybe about experiments in psychology, but really that chapter, that whole part was really about, like the nervous system. So what they were doing, what he was saying that the data of psychology is really nervous system. If you look about there, you see he'll be speaking about what is the brain, like what is the nervous system, how nervous system work. And then at the end of that part, he has a chapter called The Scope of Psychology. So first part, titled The Data of Psychology. If you look at that, there's nothing about psychology, really about, like nervous system, speaking about neurons and connection, all stuff. And then he speaks about the data of psychology. The scope of psychology. And in that piece, at the end, he was saying that, psychology is about, which is like, this, we have the psychical state, like, the feelings, the ideas, all that stuff. But in order to study that, you need to relate that to the nervous system. So he thought that, like a fundamental idea of studying psychology is really by reducing that, like to biology, to nervous system. And that was a kind of like common theme in philosophy at that time. Let's say like in philosophy of science in general. Like science till the early 20th century was. I need to raise or like. Okay. Maybe I'll raise this. Okay. Okay. Thank you. So really, like the philosophy of that time, the philosophy of science, doing science in general, was understood as reducing the higher phenomena to the lower phenomena. So in other words, like we were understood to reduce sociology to psychology, and psychology to biology, biology to chemistry, and chemistry to physics. So you see, so what you will end up having here is in sometimes this kind of a hierarchy. Now you see, like that philosophy drove science. That happened really till the beginning of the 20th century. where what we had is that we start having a kind of a different way of doing science, which is called like organicism. And at that point, like the understanding was really the laws at certain level cannot be understood by just reducing them to the lower level. So for example, in sociology, you can't just understand what sociological phenomena is by reducing it to psychology. Same wise, likewise, for psychology, you can't understand ideas by only reducing that to, to the biology or to the nervous system. And here, like that's an interesting change. However, at the early, of the 20th century, you see there are like this new school of doing science, this new way of doing science, driven by, again, this is not about history of science. Like I don't want to go into details, but it's important to understand this fundamental concept, the concept of organicism, in which current psychology functions. So current psychologists don't think their job is to reduce mental phenomena into nervous phenomena. That's not how they see themselves. They say that, we need to understand mental phenomena as a mental phenomena. Now, that doesn't lead to what can be called ontological assertions about the nature of mind, so that they don't assume that there is a soul, for example, or supernatural power that involves the mind. No, they still think that fundamentally speaking, mind is generated from the brain, but it cannot be it can be studied by reducing it to the brain. That's, that's, like the important discussion, the important difference here. However, at the early of the 20th century, like people who were studying psychology, like were falling in, like this type of this nature of psychology start to be formed. So still you have neuroscientists who are studying, like some kind of a brain, and they think that they are the basis of mind. Like, so it's natural for neuroscientists or to think of mind as something reduced to brain. This is why, for example, like there's this kind of a major paper published in 1940s by, Pitts and McCulloch. Now, if you look at the kind of traditional, like understanding of that paper, like this is the origin of neural networks. No, like, or neural networks as understood it, like goes way back. But that paper, like titled "A Logical Calculus of Ideas Immanent in Nervous Activity." So you see, like that title is interesting. Like it has like Pitts and McCulloch. One is neuroscientist, the other is logician, and they were again thinking of ideas immanent in nervous activity. You still see like it's a purely very much, reductionist approach. You see, they still think that you can reduce ideas, mental activities into brain. Now, at the 1950s, there's this idea, like there's psychologists start picking up on that thing and start saying that even though we don't believe that we should reduce mental phenomena into nervous activity, yet that these models are interesting. You see, like the model that you could look at, like at the mind, or at mind, not the brain, or like the mental activity, the idea, the thinking, the learning, as a kind of as through something called artificial neural networks. And this is why it's artificial, because it's not the biological neural networks. These are artificial neural networks that help and explains, like the mental phenomena. Now, one other component that led to the current, like understanding of neural networks, deep learning, is something called computationalism. And like the concept of machines, like is old, like is as old as like humanity. If you Google for automatons, you see like like you have semi-robots, or the notion of a robot is not a new thing. Like even like in the antiquity, they used to have like some kind of a mechanical robots. But the idea of a machine, like took in a kind of a central understanding in our modern conception after, like the scientific revolution. Again, I'm not going into that right now. However, what happened later is that the mind itself got mechanized. So we start thinking of a mind, the mental activity, as a machine. And that's through the concept of computation. Because now computation starts seeing that, you could have an understanding of a machine as a kind of a logical apparatus, an apparatus that does, that does things, that does functions through a set of rules. And that got into like into psychology, because now you have that idea of neural network. It's not anymore, like a network that does just, that maps psychical, states. It's also like a machine. It's also like computation, a computer. So you start see like these two things, and that was the beginning of the birth of a field that tries to study the mind through computational terms along neural networks. However, neural networks were not to be understood as biological networks. These are abstract networks that try, like to map, like to map some kind of a mental functions. Now that, they call that the old connectionism, and then I think there's like the famous controversy between the symbolic AI and, like and this type of group, and like so it died a little bit, and then in the 1980s it re-emerged again, and when it re-emerged, it was at the hands of famous guys today like Hinton. Jeffrey Hinton, a psychologist. So in the 1980s, he wrote like a book called Parallel Distributed Parallel Distributed Processing, the PDP. That's, like, it's important to read that book if you're interested in, like, understanding the foundations of neural network. And like, that book is 2 volumes. The first one called The Foundation, the second one is Models. And he speaks like clearly saying that I'm a psychologist, you see. Even though, like, there's some kind of an inspiration, from biology into this, but like, we're not under any constraint to, like, to be biologically realist. And that's, like, that's a kind of a concept that emerges from time to time, because like neuroscientists look at neural network, at different neurons, they say, there's an extreme position saying that the only thing in artificial neural networks is their name. That's the only thing. Like, nothing else is neural, because if, again, they give a large, body of criticism. On the opposite hand, the psychologists who are connectionists, hardcore connectionists, they said, of course. But our purpose at the end is not to model the brain, is to model the mind. You see, so we don't care whether they are biologically realist or not, biologically real models or not. Like, our goal is just to give model that allows us to give predictions for mental phenomena. All right. Now, that tension here, like, it depends on your position. If you believe that, no, neural networks should be biologically realist, that gives you a direction for, like, ideas. Because for example, if you look at the neural networks, at real neural networks, at the networks and the neurons in the brain, you see, like, they don't fire, like, in terms of, like, they don't have the kind of a continuous firing, like the value. They fire really in pulses, right? And they have patterns of firing. The other thing is that the pattern depends on the history of firing. A third, problem from the biological realists is that, really a lot of neurons, actually most of neurons, fires even without excitation. So you have a kind of a really chaotic or random phenomena there. You see, the structure again of the brain is cycles inside cycles. So we are not having this kind of a, in general in the brain, you don't have this kind of a linear structure. No, like, it's really like very, sparse, that has kind of a particular, way. Another, like, objection is that, okay, like, back propagation is good, but we don't see any kind of, like, connection that are built, like, in a backward, or signal that move backward. Then you have all these, like, questions about the reality, the biological reality of these models. However, like, that's, like, I'm saying this because that's a kind of if you're interested in new ideas, like, in that field, you could pursue that, try to build. And there are, like, psychologists that think these ideas, these models, should be biologically realistic. You see, so that's a kind of a source of an inspiration if you want, like, to do more research in this area. However, like, this, that's the nature, like, of the field. Now, one of the things also, like, interesting in this kind of a group, which is comparing to other, like, psychological schools, is that usually in psychology you get qualitative results. So the predictions are really qualitative, not quantitative, right? But in neural networks, you have a quantitative, right? So and that's, in some sense, there's a source of a sense of appealing, like, for psychologists to go into connectionism, right? Because it gives you, like, it looks like now we're doing more science. Like, you build a model, you do experiments, you measure something, right? In other schools of biology, like in psychology, like functionalism or behaviorism, all your prediction models are really qualitative, not quantitative. And if you think about it, then the nature of that research comes naturally to the research of deep learning. Like, they do experiments, they build models, they do experiments, they compare the experiments with the model. That's exactly what we do in deep learning, right? We build a model, like, we do experiments, and then we try to compare, we try to assess based on this. Another thing is that if you look at the literature of neural networks or deep learning, there's a large part of that that's clearly inspired from psychology. You speak about attention, or get that forgets. You see, like, it's really, there's a heavy, like, presence of psychology in deep learning. And that's, like, why it says you, like, if you understand that, you'll be able to properly, like, conduct better research by having, like, a kind of a solid foundation in psychology. This is why, if you're interested in doing research, go and read a little bit about the foundations of connectionism. That, like, give you, like, a kind of good, like, direction to do. Now, that was not the only group that were speaking about machine learning. There was the other group, which think that the problem of learning is different.
If it doesn't make you forget your thread of thought, could you do a summary so far, very high level, of what was discussed for people who just joined us online?
Okay.
Thank you.
So what we discussed so far is that, like, we discussed the nature of Yeah, so what we discussed so far is the nature of the first school, which is, like which is related to deep learning. And we saw that this is really based on connectionism. You see, and it has like a bunch of features. So first thing, it's really, as of understood correctly, it's organicistic or organic. I use like rather than reductionist, or it also like has a kind of it's a school of psychology, of course. You see, and the other thing, it has like a flavor of computationalism. So you look at the mind, you understand mind as computation, like the computer, and it's biologically unrealistic. There is this debate about the reality. So let's like biologically unrealistic. And an important, like book to read if you are interested, that's the PDP, the parallel distributed processing. That's like book written by, if I remember, like 3 psychologists: Jeffrey Hinton, um, McClelland, and Rummel Hart. Yes, so these are the 3 psychologists at that time. So good. Also, like look at how Jeffrey Hinton was looking at the field, like in the 1980s. I think it was probably 1986. 86. Yep.
Just want to clarify that I think Jeff more often identifies himself as a cognitive scientist and psychologist. There are very subtle differences.
Yeah.
I graduated from one, I didn't graduate the other.
Okay. So that was really the first school. Now the second school, which is really again like the problem of the mind, because you see like that paper, the paper in 1943, if I remember correctly, by Pitts and McCulloch, it really like generated again. I'm not saying that paper is the source. Like usually an idea, it's very rarely that you have an idea generated from one specific point of view. If you study the history of ideas, it will be one of the most difficult tasks for historians to identify where did that idea come. So people think, okay, like there was someone thought of that idea, but if you think about it, like it's really way more subtle. So the idea here is that paper really enforced another notion, even though it was speaking about the idea's immanent nervous system. But they say that, at the end of the day, what the nervous system is doing is calculation, is computation. And in this case, you could look now in a probably different way. Forget the neural network, forget the instruction. This is the hardware that's generating some software, and study the software. So if you are thinking about building an algorithm, you don't go and study like the hardware of the computer, right? You start thinking the fundamental of algorithm is about, like about the logic behind, like the algorithm. And that was really the second school, which is this is the nature, this was the foundation from which that paper is coming. Now there was a third school. So you see, like you have the computer scientists who are looking at that time, like the computer science wasn't really like, defined as science yet. But you have the computer scientists thinking in terms of computation. You have the statisticians thinking that, like at the end of the day, what everyone is doing is really estimating models from data. So it's really a problem. It's a statistical problem. Now, naturally speaking, these 2 schools converged. So if you look at the second school, the school that from which it's usually labeled by DL, machine as theory, it really has a kind of a very different characteristics, because what they did, that they said, like, I don't care really about the mind. It's really a computer, right? And what if my goal is really to teach computers how to learn, then really let's work it in this way. Let's define a learning problem, computational learning problem, independent of this. And the really learning problem, intuitively speaking, is that you get some algorithm, like you have some data sampled from, labeled with something, and what you need to do is that you need to let that algorithm generate a model for you, and that's it. It doesn't have the structure of a neural networks or anything like that. It's just, like a purely computational problem. And that really led to a completely different, like even research methodology, even like the whole nature of that, field changed. Because in the beginning, it was really experimental field, right? So you are trying to model the mind, So you do experiments, you build models, you validate your models by matching to reality. Here it becomes like a mathematical problem, And that really, in some sense, changed, the whole game. Because now once you have a mathematical theory, and usually, like, if anyone has studied mathematics, like, for example, look at vector spaces, You study vector spaces with very minimal structure. It's just, like vector space, with a field. That's it. You don't have any. And then after some time, like, if you look at the standard textbook in vector spaces, you start with, like the minimal structure. And then over time, you start adding more and more. So you add like an inner space, an inner product. So you have like, like now you have different structure, like you studied it. Maybe then you add tensor product. So you increase the complexity little by little. The same thing happened, like in machine learning, in that school. And this is, like what when people like look at some results, like they look at it and think, wow, that's very abstract. They, but the idea here is this. So they spoke, and this is, again, this is my understanding of the field. So they spoke about what can be called anatomy of learning. So let's call this thing anatomy of learning. And the idea here is that, that we could study learning on different levels. If we want to follow the like the regular, like path, let's look at the bare minimum needed to define a learning, which is really like, I don't need even a computation, you see. And what I need is just a function that take a sequence, we call the data set, you see, and generate a model. That was really the idea here. I'm not really adding even a computation here. I'm not speaking about an algorithm. I'm speaking about a function. So this is why, like if you, and that's the paper we're reading today is coming from that level. It's really looking at the bare minimum. So you look at your algorithm, you see, what do you define in order to formalize that a little bit? Like, let me give you some mathematics. So you define, for example, a space, a set, X. And usually people like X, because if you look about it, like those who are really entrenched in deep learning, in practice, they don't deal with X, they deal with features, right? You need to have something in order to build your algorithm. At that level, you don't care about your algorithm. What you care that your algorithm is a way to define a function, right? Then let's discard that and speak about the function. And if I was able to prove that for certain cases there does not exist a function that allows me to learn, then that's a kind of, like of now starting having this kind of understanding about the learnability. You see, the boundary of learning, which is something that, as a practitioner, you assume, you take it for granted. Like, first I'll be able to learn. And this is very interesting because, like, we know from that theory, for example, that cryptography, if it's secure, it's unlearnable. You see, no matter what type of algorithm you use, deep learning, shallow learning, super learning, you see, if you have a secure function, if I'm doing, like, say, like, I have messages, like you can build that, go open like open SSL, like this is a library for encrypting, start encrypting messages, build your own data set, you see, you have an input, you have an output, you see, and then you try to build a model that will able, like to map an input to the output, or vice versa, to decrypt. Let's take something, very simple. Use whatever structure you want. If that function is secure, then by definition, you're not able to build that. And that, in some sense, imposes, like limitations or learnability. Now, in this case, in this specific case, that was coming not from this abstract layer where I'm dealing with functions, coming from the second layer, with the computation layer, because you need to have a notion of computation in order to define computational security, that as of understood today. But the idea here.
I ask a question, but repeat my question because I don't have a So are you saying that there is a relationship between computational complexity and learnability?
Yeah. So this is kind of computation. Yeah. So the question is there like a relation between computational complexity and learnability? And the answer is yes. You see, it's really because it's really when you start, not in this paper, because learnability here is defined discarding, like a computation, or like here we're looking at even a more basic function, a function based on a kind of sets, you see. In order to have that, the computational complexity and learnability assumes that you have a computational model in which you are using to learn. And this is here, like, it comes related to the physics, because if you have a quantum computer, you'd have like a different sense of learnability comparing to classical computer. However, the results in this paper even transcend this, because quantum computer is really a way of realizing a function. But if I'm telling you that function does not exist, it doesn't care whether you're using like, like quantum or classical computation, it's by definition doesn't exist. And this is kind of an interesting point that I don't want to emphasize, but just to like say that, it seems that there's kind of a structure of reality where you have like that logical level, like at the core, at the essence, and from which you could derive, like different levels. Anyways, so let me go back. Let me get back to the, like to the first level. So in the first level, I'm dealing, I'm the bare minimum, like of a learning is that there exists a function at least that learns. And in order to define that, what we need to define first. Let me try to get this here. Yeah. So what we need to define first is really a base, like a ground base, like a set X. Which now in reality this could be like set of pictures, set of images, or set of like observation. These are really my data points, right? However, at that level, I don't care what is the structure of X. What only I care about is it's the set, you see. Now from that, I need to, again, I'm speaking about the bare minimum, like concept of learning. And the most basic thing, if I'm thinking here in terms of practitioner is really to learn like a binary classifier, like in the true false. Like I think that's the most basic thing you could do. Now that's really here certified, like or formalized, sorry, in something called F, which is a family of concepts. Now the word concept in that school means essentially like a subset of S, a subset of X, of the ground. So this is, for example, if my ground set is the set of images, then I could have the concept of the pictures of tomato by having like all these like pictures of tomato in one set. So S here, if I put ST, could be like the set that refers to the pictures of tomato. Now, usually, and that's an interesting thing. It's important to understand that in order to understand the formalization, is that when you build a model, when I'm publishing a paper about a model, I don't mean that model works only on the data set that I tried my model on. So for example, when you look at a paper and see like I tried my paper on GANs and CFAR, you see, and they achieved this result. That doesn't mean, okay, like the conclusion of the paper is not, I have a good model now for MNES and CFAR. That's not the conclusion. And that's like, I don't know to go into that detail, but I think that's it's important to understand the epistemology, like of publishing in machine learning. Usually in the deep learning thing, like all papers, majority of the papers are really following an inductive argument. So what they want you to convince is that there is a class of problems in which you could use that model in order to learn that class, or in other words, like to learn any problem in that class, to learn any concept in that class. And how do they convince you of this? Inductively, they try in 1, 2, 3 different sets. You think they are from the same class, you see, and then hopefully they succeeded at letting you believe that first that the results of their, like publication, and second, that what they did is good enough for you to make the generalization. So every, like paper, more or less, you see, in the deep learning is really published with that inductive assumption, you see, so explicitly or implicitly. And this is why, like the quality of the paper really can be assessed by how successful were they in convincing you that generalization holds. Now, even sometimes, like like if you have a completely new approach, like again, like it's a little bit, but it's important, I think, to understand this. If you're like, if you have GANs, you see, like when that GAN was published, if you just tried that with just few experiments, like people will be skeptical, you see, like especially that in the beginning when you publish a new model, you're not able to do a breakthrough. So what you need to do next is to try to justify your induction by a theoretical result. Now, the theoretical result doesn't prove that your induction is valid. It's really just a means to convince you that is really, like it's worth to be published. And the publication really means like it's worth to be tested, because over time, like the models that are successful will, dominate. So there's this kind of a sociology about, the community of machine learning, you see. But the important point is that the theory of machine learning is not really, doesn't function the same theory of the community of computer science and statisticians. They are not proving theory because they don't have even a kind of a deductive system. You see, what they have, like, they build a model, try to convince you that this model generalizes to other problems by doing experiments on one hand, or by having some kind of theoretical, like proofs. Is the essence of that yet, however, is not really to convince you that the model will function by proving that to you. That cannot be proven. This is not what the structure or like hierarchy of the computer science community, because there they have a deductive system. So they were dealing with mathematical problems. So they look at the problem of learning as a mathematical problem. They start with axioms, definitions, and from there they start proving theorems. And each theorem is really, like a piece in the way, like in the building they are building. So let me get back to this. So like, so what do they do then? If you understand this, then you see like when you have a model, you don't deal with a model at only one specific problem. You assume there's a class of problems, to which that model works, you see. And this is really in the simplest case, if looking, let's say, for example, at the case of, building classifier for images, we have X, this is my ground set, you see. Now I can form subsets of X, like this is subsets of picture. Each subset is called a concept, which really captures, like one problem that I'd like to learn. So for example, you could have like the pictures of tomatoes, a picture of, like potatoes, and then you are building a classifier. Sometimes you train your classifier on tomatoes, right? You want your classifier, you see, to work on tomatoes. Now, usually, again, in the DL, you speak about, you see, like we have different concepts. We have model, we have training algorithm, we have hyperparameter search, we have all that stuff. in that thing, you know, like because of the nature at that level, I'm speaking about the most basic level. I don't need really, you know, like to look at all this. So what we do is I define something called learner. So learner G is, you know, like is really a function. Again, it's a function. It's important to understand, you know, like it's a function that takes a sequence. So, you know, like I'll call that, you know, X star. So X star is a set of sequences from X. So these are your training, you know, like data, and hopefully emit something in F. Now, in reality, like I'm misusing the notation. Like if you are speaking, like it emits something from something called a hypothesis space. You see, so you emit something from a hypothesis space. Hypothesis space here really. Let me put it in this way. Let me try in the beginning to be a little bit formal. So you see, like so we are here have H, big H. So this is a kind of hypothesis space. So each element in the hypothesis is also a subset. You see, so you see, like so what the model does as a learner, because when you end up like if you're like at the classifier, a classifier will be you give an input, it either say like true or false, right? That was a classifier, right? That could in some sense define a subset of the images that has the you know like an item of 1, like a value of 1. You see, so we could any subset could be you know like transferred to an indicator function, a function that takes an element and returns 0, 1, and vice versa. You see, so in this talk we'll be using these two concepts like interchangeably. Any subset, any set could be represented by an indicator function and vice versa. An indicator function gets an item and 0 and 1 is also like defines a set. So if you think about it, you know, like your learner, which includes really the training, all the, you know, like the hyperparameter search and the model and the optimization, all that is really now ended as a function. It takes, you know, a subset, it takes a sequence of training data and generates, you know, like a set. And you hope that that G learns F. F is a class of concepts. So for example, in the simplest case, assume like I just interested in the potatoes and tomatoes. You see, so I have here F really contains, you know, like two things. The first ST, which is the set of potatoes, and SP, vice versa. So ST is a set of tomatoes, and SP is a set of potatoes, right? ST is a set, SP is a set. Or ST is an indicator function. It gets an element from X and returns 0, 1. These will be used here interchangeably. Anytime I'm using a set, I could take the, you know, like liberty and deal with it as an indicator function. So you see, like that's a kind of a bare minimum thing you need in order to define a, you know, like a learning algorithm. So now in that mode, if I'm able to tell you that there are things that cannot be learned, if there are things that cannot be learned, then it doesn't matter what you are using, deep learning, you know, like shallow learning, super learning, you will not be able to learn it. Whether it's quantum computer, classical computer, post-quantum computer, it will not be able to learn. Like there's a kind of fundamental limitation on learnability in that realm. The paper we're dealing with today falls under this. Now, I hope that you know, like that it's important because many people go look at their, like they look at this, and again, like not all theoreticians in that field working at that level. So you have people working here, like, and the very abstract thing, and mostly these people are coming with fundamental results, either with severe limitations, you know, like of learning. Because you see, like anything you prove here, it has an impact on everything else. If you define that, for example, for some problem here, you would have has some kind of a complexity. This is the notion of a dimension. Many people like misunderstand that because dimension is coming from that level. The VC dimension is really a concept defined in this. So, and VC dimension is really related to the size of the training set you need in order to get that function learnable, right? Then that means really, if you have like a VC dimension high for some class of problem, then again, it doesn't matter using neural networks high, you know, like you'll end up need large number of you know, like large size of training data. Now the VC dimension by definition is not something practical you go and okay, I know, like, you know, give me the VC dimension of MNES. You can use it in this way, but it gives you, it starts defining the concept in which you're thinking, in which you think about the problem of learning. So instead of trying blindly, go trying soft learning by just trying building models, now start having a structure here, you see. And this is here, like what ends up happening usually, that when you have a problem that's difficult.
Sorry, could you just spell out what you mean by VC dimensions?
Yeah, so VC is really a Vapnik-Chernonikov, this, if I'd like to know that, you know, like a number, which is in some sense, again, it's a dimension defined in that model. It's not, you know, like this big. So if you have in order to find that, allow me, like I'll get back to this question. So essentially, you know, like in that level, you know, like I'll get back to like the entity of the concept of interest is really this F. A lot of work is happening with this F. That's the family of sets, because that's what defines the complexity. Now, the other constraint, like I explained almost everything. The other constraint, because usually when you talk about training data, you assume that these items are coming from a probability distribution. Yet you don't know that distribution. So that distribution is unknown. You want to say something?
No.
Okay. Okay. Yeah. So that distribution is unknown, right? So the assumption here is that like these training sequences, there is some P, unknown P. I don't know what P is, right? And this is why, it's interesting that we are able to get results with this kind of a severe limitation. Like, if you think about it, it's really something really interesting. You know nothing about G. You know even F, the structure of F. You don't know P, and yet you are able to arrive at concept like dimension, you see. So in order to explain a bit what dimension is, the entity then, because of this understanding, P is not interesting, right? You see, I don't know P. I don't take P into my, analysis. Sometimes, I talk, if I define some kind of a, slight constraint. So for example, in this paper, they assume that P is finitely supported. That means, the distribution are really defined on finite sets. Your concepts are finite sets. However, X is infinite, anyways. So, but sometimes they do that. But besides that, because in order for this to be meaningful, you need to deal with the reality of the life. Most of the time, always you don't know P. I mean, let's face it, you see. So that understanding, once you have that, you now start building these tools. So the entity of the concept of study at that level is really the F. That's, that's really what defines, the complexity of so it's F and X, because F depends on X, but it's really F. And this is why, if you start having this kind of notion, so you define a way of learning, for example, you have something called back learnability. And in that model, and under that definition, so really capture in some sense this kind of a classification problem. You see, you speak about the complexity, how much data set do I need, in order to get F. So I'm not defining F VC mathematically. I'm defining it in terms of the usage of that. And I think that's kind of a good way to introduce that. So one of the uses of the dimension here is, in some sense, to allow you to qualify how much data set, what is the size of the sequences you need in order to properly learn, a concept from F. It's independent of P. That's the main assumption. You don't look at P. You see, you don't look at the distribution. I say whatever, as long as you're giving me a rational distribution, not just giving me all the always the same thing. I'm just giving me something a representative really. How much data set, how much sequence, and that's what VC dimensions capture. Slightly. However, the problem of this paper, of today's paper, is not really so again, it still have it's a learning problem, but it's not a regular learning problem. And there's a reason for that. If you are trying to study the limitations of a concept, then you try to study that in the most severe cases, in the more severe conditions. So what you do really, if I want to see I want to prove that there's things that cannot be learned, you see, imagine the most complex situation and try to learn that. You see, because you want to make it easier, right? Now, at the starting point, you go there, and then over time, what you try to do is that you try to relax your assumptions, little by little, in order to, to identify exactly the contour of learnability. You see, so what you do at the first shot, you go to the most extreme cases. See, if I want to learn something in infinite sets, it's not realistic. You see, the goal here, that's a research program. You need to understand this. We have a research program. The starting point of that program could be the easiest. Let's look at the lowest hanging fruit. That's what we do really in machine learning. Start with model that give you kind of a sense about the data set, right? So exactly what you do here is this. But on the theoretical level, you take your axiom, take your definition, imagine a very severe situation, and go stress testing your axiom there. See if you can able to learn that. Most probably you will not be able. And to be honest, in some sense, they say it's surprising that we get that result. But if you think about it, okay, you're trying to learn something in that depends on the cardinality of the real numbers. What do you expect to get? You see. Now the idea here is this. So in order to get a little bit closer to the paper, and the structure of the paper is this. I'll just give you the structure of the proof, and then we'll see if I have time to go into the proof. But okay, 714. Okay. So the structure of the proof is the following. You see, you have something called ZFC, Zermelo-Frankel with the axiom of choice. this is really the the standard for axioms for mathematics. And by that I mean, like, if you go everything you study in mathematics, let's take probability. Probability, in order to define probability, you need the concept of a set, a concept of a function, because that's what, like, it's a space with a probability space, right? So, like, you have a sample space with a probability function. You see, so that's what you need really. And function points out that you need sets. So set theory is really at the foundation of mathematics. All the other branches, anytime when I say all, if not really all, like, like in the, like, it really means like most, you say. That's, I take it as a translation thing. So most of, like, all the mathematics, branch of mathematics, it really boils down in the classical view of mathematics to set theory. Now, if you are able to find, like, some set of axioms that capture set theory, then in some sense you are capturing the whole mathematics. These are the most foundation things. So what he did, what they did, like, in order to understand this, you need to understand that, and that happened, like, early in the 20th century, for a reason that has a lot of philosophy here, and we'll try to hold myself from going there. So, but the idea here is this, you see, like, let me give you 1 minute, introduction to the subject, you see. Like, my goal really is just, like, to get some interest on you, like, to go and read a bit about that. So really, like, mathematics, historically speaking, was understood, the concept of mathematics understood as real entities. So when I speak of a number, they're understood to be some kind of an abstract realm that, hold that. So mathematics wasn't really just, like, an operation in the mind. It used to capture some level of reality. Now, with the like, the scientific revolution, that idea collapsed, and people start thinking that what exists is only the physical realm, more or less. And they have started having, like, problem in foundation. Like, if that's what exists, what does mathematics represent then? You see. Now, in the early 20th century, there were these kind of schools. So one school is called logicism, which is really trying to reduce mathematics to logic. So they would say, like, what mathematics is really about logic. An axiom, system of axioms, like, from which you could deduce results. Another school called formalism, it's about, no, it's really about set of symbols that you are trying to apply rules. Anyway, that's a kind of like a 1 minute description for long. But the problem here is that logistic, program, in some sense later, like, okay, all mathematics is about logic. Now, what ended up happening is that if you take that view, that, mathematics is logic, then, of course, not all mathematicians were happy with that. Gödel wasn't happy with that. Gödel is Platonic. He believed that there is some reality about mathematics. And what he proved in the two famous incompleteness theorems is that, first, if you have any system, any logical system able to capture decent amount of arithmetics, like, the regular arithmetic, like, summation, like, then there are theorems in that set that cannot be proven, like, in these axioms. Now, this means that, like, okay, there is a theorem, there's, like, a formula that, like, it's either true or false, yet you cannot prove it, neither true nor false. So that theorem doesn't, like, arrive from that. And what he proved, was like, that this ZFC really, like, sorry, not the ZFC, but that's, that's one of the incompleteness theorem. Now, later it was proven that, and Gödel was interested in this problem also, is that there's this problem called, like, the continuum hypothesis, which is really about the size of the real numbers. Now, let me give you, like, and that will also help us in the proof, like, of this theorem. So usually when you think about sets, like, for example, I give you a set of 1, 2, 3. What is the size of this set? It equals to 3, right? So it seems that the numbers could be used to represent size of sets, finite sets. So, like, a size of, like, any set that has a kind of, like, size of n, they are all in some sense equal in the sense that, they could always find one-to-one mapping between all these sets. So what ended up happening later, what ended up happening later is that, like, so we have, like, the natural numbers, like n. That's not n, but anyways.
Looks like it.
So we have the set of natural numbers, you see, and that set, like, it's infinite, right? So the size of that set is really bigger than any set. So what Cantor, and that's, what the famous method did, is that he said, now we could start even, generalizing natural numbers into, like, infinities. So for example, by defining the same concept, like two sets have the same size, if we're able to find one-to-one mapping between these two sets, you see. So if I'm able to find, like, all the sets that are, in some sense, bijective to n, then I'm defining, like, this kind of infinity. So he was able to say, like, okay, n, and he was able to identify, like, the set of Q, the rational numbers that, these two sets, like, are really, like, identical. Now, that would be like a counterintuitive for people. So let me give like a simple example. Like, if I speak about the natural numbers, so I have 1, 2, 3, like to infinity. And then I have the odd number or even numbers. So I have 2, 4, 6, right? On one hand, it appears that the even numbers, even though both sets are infinite, but even number is a subset, is a proper subset of natural numbers. However, if you look about it closely, in reality, this is a kind of a natural number in disguise, in the sense that n could be written as 2 times 1, 4 could be written as 2 times 2, 6 could be written as 2 times 3. So it's really just a renaming of natural numbers into even numbers. You see, and in some sense, like if, in other words, I'm able to now to identify one-on-one between the set of like natural number set of even numbers. You see, because what the even numbers turn out to be is just like kind of natural numbers in disguise. And that concept, the concept of having mappings between infinite sets. In other words, now I could say, according to this, that the size of natural numbers set, even though it's infinite, is equal to the size of the even numbers. And then, like later he was able to also prove that not only this, but any number, like I said, like a over b, these are the rational numbers, are also countable. Like, or like they, in some sense, they are again a renaming, but clever one this time. Like with the, with the natural numbers. So again, and any set, that has a kind of a bijection with natural is called countable, because now natural set has 1, 2, 3, so you could start counting them. So this is kind of a countable set. And after these two theorems, we're like, is it possible that all the sets, all infinite sets are really like, just renaming of this? And there's a theorem, I don't want to go into it right now. You see that the real numbers are known. They're not really bijective, to n. Like there doesn't exist a bijection between natural numbers and real numbers. You see, so now real numbers are clearly bigger than natural, because natural numbers on one hand is a subset of real numbers, yet there does not exist any bijection between these two, right? And now we start seeing like, okay, now we start arguing like there are levels of infinities. So you have the first level of infinity, which is called usually, if I'm using like a technical term, it's called Aleph 0 or Aleph null. This is really the infinity. This is the size of natural numbers, you see, or any set that's bijective to natural numbers. Yeah. And then another theorem, I'm going into the details of this, you see, is that, usually if you have any infinite set, you can define a strictly infinite set that's strictly bigger than it. So there's kind of a sequence of infinite sets. So you have Aleph 0, and then you have Aleph 1, then you have Aleph 2, and so on and so forth, right? Now the question becomes is that, we know that R, the size of that infinity, is certainly not Aleph 0. We know that, it's not countable. Is it Aleph 1? Which Aleph is it, right? And that's called the continuum hypothesis. In other words, like, is there one other formulation of that? Is there some set that's really large, strictly larger than natural numbers, yet smaller than real numbers? That's another formulation of the continuum hypothesis. And the answer, yeah.
What are those again?
So these are generalizations of natural numbers into the infinities. So Aleph 0 represent, because what we started with is this: any number, any finite, like 5, represents really all the set that has 5 elements. Right? 6, although it has 6 elements, right? Aleph 0 is bigger than all finite number, right? You see, and it represents the sets that has countable numbers, is like n, natural numbers, right? Aleph 1 represents sets larger than natural numbers, strictly larger. You see, so you see that there's this kind of a natural sequence. Now, the question is, what is the cardinality? These are called cardinal numbers, by the way. So what is the cardinality of real numbers? That's a question, right? That comes out to be like something called the continuum hypothesis. And the surprise is that it's not provable in Zermelo-Frankel, like with axiom in ZFC. You see, that theorem is independent on this. In other words, you could assume that it's true, and you don't have a contradiction if this set is consistent, or you could assume it's false, like both are like the same. Now that position in which we are finding itself, like in that there are, because in the beginning we're assumed that start having this kind of theorems that are maybe like imaginary theorems, sort of, you see, like very abstract. But now we start having some kind of more real theorem, like I can't really even identify or know what is the cardinality of a real number. You see, and that really has a kind of a lot of philosophical consequence that I don't want to go into right now.
In the next 5 minutes or so, whenever you think is good.
Okay. So essentially, like that was really the thing. Now the paper read. Now let me. I was planning to explain the structure of the paper. So this is okay. No, maybe I don't need to. draw either. So what I'll do there is, like this. So now you understand what continuum hypothesis is, So the structure of the paper is as following. So we have the foundations of mathematics, From that, I'll use that from that, with quotations, From that we know that the continuum hypothesis, this is like, like usually is undecidable. Like you can't really, like decide whether what is really the cardinality of the R, or whether it's any one of this. Like it happened that, really the cardinality is really bigger than any cardinal number. So as undecidable. Put it this way, undecidable. So now what the paper does is the following. So it showed that if it forwards some problem, you see. So let's say like we have a problem, it's called like F star. So you have some class, you see. From that, if you are defining that it's learnable, if, for example, if it's learnable, if that class, they define some kind of specific machine learning problem, you see, some specific set, they construct that. It's artificial. It's not, of course, practical because of all the things that have been speaking about. But if it's learnable, in the sense that there is a G that is able to learn the concepts from sequences of that, then that leads really to like that we can define in some sense a limit, like on the cardinality of R. But we know essentially that like CH is undecidable. You see. Now the question here, what they really did is that they proved there's an equivalence in the sense that like if this is learnable, you see, then the cardinality of real is finite. You can identify like an upper limit of that, right? If it's unlearnable, and thus like there does not exist, like a G, then the cardinality of the real is all bigger than all the, like the cardinal numbers, right? Now the fact that the CH is, and because of the equivalence of these two, you see, and the fact that CH is undecidable means that the learnability of that class is undecidable. You see, so they didn't prove that there exists or there does not exist. What they said here is that there does not exist a proof. You see, that's something unknowable. You see, now. I'll say one word, like and finish with it. Like if you think about it, like in the early 20th century, like the nature of mathematical realm was about, in some sense, formalized. David Hilbert, one of the most famous mathematicians at that time, he was like, I was saying something like, wir müssen wissen, wir werden wissen. In some sense, it means that we must know, we will know. You see, that was his thing. Like he didn't believe that there exists something like, undecidable or unknowable problem. He was like, of course mathematics is knowable. Of course, And he was even going one step further, saying that you could find an algorithm, like that allows you to prove any theorem. So give me a theorem, give that to the algorithm, like it will be able to give you a proof. It'll tell you whether it's true or false. In some sense, the mechanization or automation, that's the modern word now, automation. There's what mechanization. The mechanization of scientific, like discovery in mathematics. Now, the outcome of this, was in some sense, again, there's a debate between philosopher and mathematics, you see, but many people think that this is in some sense like a blow to his program, you see. Now you know that there are things that cannot be proven. And that has a lot of implication toward the theory of mind and philosophy of mind. So I'll stop here, take a few minutes, and then we'll come back.
Are there any questions before we take a break?
Yeah, some things are unprovable because mathematical tools are finite and incomplete, right?
Sorry?
Some things are unprovable because mathematical tools are finite and incoherent, like they're incomplete, right?
Finite and incomplete?
Yeah, like in order to assert that something is provable or not, I think you need to have a comprehensive system, and that's not possible because we have a finite.
You just don't follow from ZFC. There's 9 axioms there.
Yeah.
They don't imply the statement.
Yeah.
That's what undecidable relative to ZFC.
Yeah.
That's what's happening.
So actually, the incomplete statement has few like flavors. So one of this is exactly this. The other thing is that even if you extended ZFC with any axiom, there will still be some kind of theorem that's fundamentally, like unprovable. So, and that in some sense related, by the way, to what I say, like, because if you're speaking about infinite, like set of axioms, then that's, like a theorem that I cannot say it holds or not. You see, like, for all the thing here we're starting, and then go like science or logic is about like organization of knowledge. Like you try to reduce the whole body of knowledge into like some kind of say axiom from which you deduce your results. You see, so finiteness is just something. Like if you speak about infinite, I was like, I don't know, like that's not something that
So I want to just clarify the understanding because it's like so informative speech. So first of all, the idea is that we have this framework which is called CFC or whatever framework that we have in order to learn in order to understand the environment. And here we have this mathematical environment that we try to understand. There exists some statements that we cannot decide their validity, whether they are true or false. Is that correct?
Yeah, so let me just say, like, the idea here is this, like, usually any science needs to start, any mathematical field needs to start
with some set of axioms.
With some set of axioms. So no matter what your axiom is, if they are, unless they are like very small axiom that doesn't really prove a lot. So like if your axiom can only prove one thing, that's it. You see, like I'm not speaking about trivial axioms. I'm speaking about axioms that are really, general.
Euclidean geometry. It's
yeah.
Some axioms.
Yeah.
In this axiom, we can try to understand some kind of shapes or whatever based on that, and then there exist some types of shapes that this type of axiom cannot correspond to, and then so.
Yeah, if you want to by analogy. You see,
exactly.
Yeah. Yeah.
So, what do we mean by learnability?
Okay, so learnability here is as this intersection is the existence of a function that when it gets a sequence sampled from set, it's able to learn the relevant concept. Right. So you have a concept. You see, let's say like picture of tomatoes. Like sampling. Like samples. Some of them are tomatoes, some of them are potatoes, labeled. Right. You see, learner is a function that's able to get that sequence and and learn that concept approximately. You see, all these are approximations, right? So the larger sample set will be the more accurate your concept is. You see, if we have something like that, we call the problem learnable. If the function doesn't exist, I'm not speaking about an algorithm. I'm speaking about a function. If the function doesn't exist, which means like any algorithm doesn't exist, then that concept is called unlearnable. You see, so undecidability of the learnable is that the theorem doesn't say that I have unlearnable concepts or unlearnable classes. That's not what the problem is saying. It's saying it's like there's this class which you cannot decide whether there is like G or not. So even if I give you a G, you will never know this is really learned that class or not.
So how we can validate that idea? What this continuum hypothesis?
Yeah. So the proof of that idea is really by trying to. So let me just to make like validating means like how can I prove that there is such a thing? So what the paper did that they constructed, of course, an artificial class F star, you see, such that they proven that the existence of a learner here is equivalent, like to the continuum hypothesis, to proving some statement of the continuum hypothesis. But because the continuum hypothesis is undecidable, we know that. You see.
What do you mean by undecidability again?
Undecidability means a statement is undecidable if not able to assert its correctness, its validity, true or false. It's true or false. Yeah, I cannot assert that. You see, that's undecidable, right? The existence of a learner for that specific problem is equivalent to asserting, like the truth of that statement. So you see, like there's a kind of an equivalent. Now I understand. Let me put it like doesn't when I was reading that first time, that was a lot to take. You see, so and I think like the goal of this not really to go into the proof. Like I'd like to go into the proof. You see, but the idea here, the essence here is really manifold. So first, like to give you like kind of a different understanding of different fields, and then try to understand the relation between this kind of a theoretical machine learning, the so-called, and your work.
What's the difference between your X and your F in the construction of the learner?
Can you repeat the question?
All right, so the question is, what is the difference between X and F in the
Construction of the learner.
in the construction of the learner? So really the learner takes, like a sequence from X, and ideally they will input something that approximates a concept in F. F really is a class of concepts. It's a set of concepts. Each concept is a subset from X. Let me repeat this slowly.
But isn't the union of the subsets of X equal to X? Subsets of F equal to X?
Yeah, not necessarily. Depends on F. You see, like depends on what is the class of problem you're interested in. You see, like the class of problem you're interested in image processing doesn't equal the class of all possible images, right? So, for example, if I'm really interested only in face recognition, you see, that class of concepts really doesn't equal to the all possible images.
X is the set of
all images, yeah.
Okay, thank you.
See, F is a set of class of concepts from X.
So just to clarify then, this is saying that I can construct a data distribution such that if I run, like such that there is no machine learning algorithm or model that I can train on it, like I will never be sure if that model has correctly learned that distribution.
Exactly.
So in other words, there are special distributions that I can make that like I can never.
I'll be honest with you, this is a kind of theoretical distribution. So like, moving that to something practical is a different story, right? But in theory, there exists something that that has this, property.
No, I think the idea here is that in theory, you don't know that if such a distribution exists or not. You can decide that you cannot tell the existence of that distribution based on the ZFC AISM system.
Okay,
I don't think it's constructive.
The
argument is existential. It doesn't like actually produce it for you.
Right.
It just reduces that to the continuum hypothesis.
So let me clarify here. Like the problem, the probability, and the f and x are all well defined. I know that if for this x, for this distribution, I can identify the distribution, the probability distribution, the x and the f. That's well known. I can give you the problem. I cannot tell whether for this specific problem I can find a learner or not. So the statement is about the learner, the learnability of a set, not the existence of a set that's learnable.
Right. The existence is different from the buildability of the model, right?
Yeah. So I know that the set exists.
You cannot tell the existence of the model, let alone building it.
Yeah. Let me put this way: like the theorem here in this paper is not about the set. The set exists, is well defined. I can tell you what the set is. The set is the numbers between 0 and 1.
No.
You see, the family.
The set exists.
Yeah, the probability is really this, because like let me put it this way, like in here, like I assume that I don't know the probability. I know the probability is one that has a finite support from x. So like take any finite set from number between 0 and 1, and that could work. And the condition that you don't know that probability, because if you know it, that's not a real like machine learning. Usually you don't know the probability. You see, but the probability exists. It exists. I know the class. It's finitely supported probabilities. You see, the class of the class of concept, the class of finite sets. All that I know. The problem is clearly determined. The question is that I give you this problem. Can you find a function that's learner? Here you cannot answer whether you cannot or not.
That's what I'm talking about.
Yeah.
The can you find function somewhat telling you like how if it exists, can you construct it? That's two questions. I'm just saying there's two questions.
Yeah.
I'm just saying the existence of the function
is undecidable.
Is undecidable.
Yeah.
Let alone like constructing it.
Yeah.
So
but I was translating this to some sense like a practical language. So think here that even if you believe that I have this, if I constructed this algorithm, right? You see, let's say like I come up tried it in some sense, trying the kind of theoretical deep learning on that, like model, right? You see, is that a model learner, like a learner for this? I can't tell.
But if I were incredibly lucky and I had such a function in my hands, I should be able to tell, right? Whether I should be able to verify whether it was or not. I just keep sampling from the distribution and see if it gets it right.
See, I'll be mean and tell you like the true answer. You see, and the true answer is this: it depends really on what you understand by mathematics. Because if mathematics really is about, and this is like thing here, if you think that because your assumption, understand there is some kind of a mathematical entities independent of the proofs. You see, like so you think like like that function could exist. You see, like like I could get lucky. There exists in reality, if I to paraphrase your statement, there exists in reality a function. You speak about a reality, mathematical reality, you see, and you say that there exists a function there, yet I cannot able to prove whether it's this or not. So I could get lucky in theory and find it, right? You see, that in order for that statement to be correct, you need to assume that there exists a mathematical reality independent of the proofs.
Yes.
But if you're a logicist, you see, or formalist, or intuitionist, like all these kind of modern things, you'd have hard time arguing with this, right? So this is why it's interesting, this paper, because like, if you, at the beginning, that's what it was like, I was exactly thinking in this thing, but the assumption here is this, right? Which is the big assumption in philosophy and mathematics, especially at that level.
Let's take a quick break and you can digest and come back with more questions for discussion. Sound good?
Yeah.
Clarification, starting off, where we left off.
Okay. So I'll start from here.
So I'm trying to sort of see if I can connect it to something practical, but does that, or what they have shown, does that mean that we cannot have any AutoML algorithm that gives us any guarantees?
Okay. Yeah. So the question here is that, like, does this paper show that we cannot have any AutoML algorithm that give us, like any guarantee? And so that's a tricky question. Like, I'll tell you my position on that question. Again, like, this is my personal opinion, you see. So in like that, first, that result is very theoretical. You see, like the goal here, and again, like you need to look at this, this is the first step in a research program, you see. So this is why I find like very difficult to come at, like, but regarding this question specifically, I think a closer theorem that could give us insight about the AutoML question is the no free lunch theorem. It's another result in the theory of, of machine learning from that school that comes, again, from the same set theory. Like, so again, we're still at the same basic level. And the no free lunch theorem tells us, like, there is no model that's superior to on every data set. In other words, like, all the models are equivalent. For any model that performs over than the average on some set A, there's another set that the same model performs under the average, you see. And that means, like, really in the sense that if you have an AutoML system, you think like this is the AutoML system that will solve all the problems, in that sense, it doesn't exist. That's, what the no free lunch theorem asserts, you see. However, that doesn't mean that you could have some kind of a domain, that which AutoML system could perform, over better than average. But the thing here is that, like, if you want to, that doesn't mean that that would be the best model. Like, the thing here that if you want to solve that problem, you need to be, like, more specific. However, I'll add one more point, like, is this. So there is a kind of a philosophical element here in the following sense. If you believe that minds are machines, then the no free lunch also applies to the mind, you see. And in this case, it tells that, if you're learning, you see, if you're learning something, that doesn't mean make you better on everything. It's really like you're just shifting, like your area of expertise to one area. Now, that assumes that you're already taking the view that mind is a machine. If you don't take that view, you see, then that doesn't apply to you. But there's like this kind of question, which is similar to quantum mechanics, like where do you set the boundaries between the object and the subject, right? If you take everything into like the thing, of course that applies to you, right? But the idea here, I don't think that, I think a more relevant theorem is the no free lunch theorem to address that question. Okay.
So just like to clarify that AutoML thing, as I understand what you've said, then no free lunch would apply if we were considering the set of every possible universe with no constraints whatsoever. Like, anything can happen. In the universe that's real that we inhabit, no free lunch definitely doesn't apply because there are some like latent things that do apply, and it's possible that this thing doesn't apply in our real universe at all either, because maybe there's not any kind of process that could generate one of these undecidable distributions.
I like this comment. That's that's a very fair point to make. You see that I exactly agree. And this is why, to be honest, like when I was if you look at that, because in some sense involved that you are learning random sets. So like no free lunch theorem, part of that is random sets. But we know from a lot of theory that really random sets are really, we don't deal with random sets. Really, we deal with the current universe, which is really very structured, actually very smooth. That's what allows like differential calculus to apply, because like we have like on a smaller scale you have a kind of a linear behavior, you see, and it's in that universe we're applying like machine learning. So I agree with that. But that, however, doesn't imply that like there is a kind of a superior universal like learning algorithm like AutoML on that. You see that I still believe that there is a variant of no free lunch in this ordered universe. That's like my assumption. Now. I'm not sure if I'm able to, if I want to, I'll take a few questions. I might come back to that question. You see, like there might be another way to reason about this through the undecidability of these questions. Because if you think about it, like if the mind is a machine, and if there is kind of an inherent question that we cannot solve, then that applies also to, if for machines there are inherent problems that cannot solve. For computers, there are fundamental limitations, not coming from the free lunch theorem. It's coming from really from the learnability. you see, then that might imply some position, like some limitation on the machines. However, we still have the question of, do you think mind are machines or not? That's, like, how do you interpret that? Okay, I'll take it. Yeah.
So I'm still trying to digest it. Like,
Yeah.
the question of about the continuum hypothesis. Can you again elaborate on it? What does it exactly state, the continuum hypothesis?
So the continuum hypothesis, there are different versions of it. Like this simplest version is that, like the continuum hypothesis is there does not exist any infinite set that's locked between the natural numbers and the real numbers. So you have the natural numbers, you see, you have the real numbers. We know for sure that the real numbers are bigger than the natural numbers. That's different, right? We know that, right? Is there any set that's in between? And this is why it's called continuum hypothesis, because the real numbers represent the continuum, right? Is there a set that's really larger than the natural but smaller than the continuum? You see?
The definition of infinity is like that question, because both of them are like, the definition of because both of them are like going to infinity, but you say that this infinity is smaller than that infinity, but then
yeah,
comparison of infinity.
Yeah. Like, so the comparison of infinity is the sense that, like of the extent of a bijective function. So for example, so it's a one-to-one function. You see, so for example, if you look at the set of natural numbers and set of even numbers, on the apparently the even numbers is a subset of the natural numbers, right? But if you look at the even numbers, see, like they are just renaming of the natural numbers. So in some sense, they are really equal. In other words, I could find a one-to-one mapping between the real numbers and the natural numbers and the even numbers, right? And that means they have really the same size. If they both are infinites, they have the same size, right? However, I cannot find, there is a proof for this. There does not exist a mapping between the natural numbers and the real numbers, you see. However, I know that the natural numbers is a subset of real numbers, right? And this is why then we say, even though both are infinities, the infinity, or to use like a more technical, the cardinality, which is really the size of a set, the cardinality of an infinite set is bigger, of the real number, is bigger than, like the natural numbers. Now the question is, can we find an infinite set that's between these two infinities? You see? And that's what the continuum hypothesis is. A statement of that hypothesis.
So it says that there exists or there does not exist.
The continuum hypothesis?
It says
you can take like a true or false. Like say like it doesn't exist. Like they say like, no, we believe that the continuum hypothesis, the real number.
There's no continuity between these two infinities.
Yeah, there's no continuity. Like the only thing that comes after natural numbers is real numbers. You see? Now that I cannot prove. Sorry, go ahead.
The existence of that is like a question. That the existence of such a set is undecidable. That's an undecidable statement.
So how does it relate to machine learning?
I was going to say, can I say this? Do you mind stating the EMX, the definition of the EMX learnability? Because seeing that, I think it would help. Just seeing what kind of animal we're dealing with.
Okay, so I'll do that. I'll try to answer that first. Then I'll do that. So really, the thing here that what they did, and maybe I'll follow your advice. So what they did here is this. Like this is how they relate. Now I'll give you a bit more detail, but hopefully that thanks. So what they did is that let X be, like the set of real number between 0 and 1. You see, that's, like my X, you see. Now, I'm learning concepts from X, you see. So F, which is the family of concepts, this is called, like Fx fin. That's, like what they use. This is really the set. F is a family of all finite subsets from X. So for example, if I have this set, 0, 0.3, and pi over 10. That's a finite set, like it has 3 elements. This is, it's a finite, right? It's a subset between 0 and 1. And that's, like an element in fine X, in the F, okay? So now I have X. The concept of, the class of concept I'm learning is really the set of all finite subsets from X, okay? That's what F, this is the F that I'm interested in learning, right? Now, what they define also P, like a family, so because usually in learning, you have like, these are the 3 concepts, the 3 important, like elements, the probability distribution, the X, the ground from which you're getting your samples, and really the class of concepts you're trying to learn. And probability here is really probability of something called finitely supported. In other words, like what you're, like your distribution, there is the one distribution from which I'm giving you the elements. You don't know the distribution. What you know about that, it's really giving you from a finite set. You don't know the size of finite. It could be like 1 zillion thing, but it's still finite. You see? That's the three elements, right? You see now. I need to look closer at colon. Anyways, so you see, like, this is X, this is P, this is, like F, you see. Now, the problem here they are really in EMX is a little bit slightly different from, like regular problems. Because usually in traditional machine learning, you have labels, right? So you don't have only X's. You're telling me these are in your class and outside the class, right? Now, the problem here is different in the sense that what they want you to learn is a class that approximates as much as they can, like the indeed. So it's in some sense like you can look at that as a kind of a form of unsupervised learning. You see, I'm just giving you samples. Like they have an example in the paper saying that if you look at visitors that are visiting website, you don't know anything about the visitors, nothing. You see, the only thing you know that whether they clicked on the website or not. That's what you are getting on the ad or not. So you need to show an ad, you see, and you need to maximize the number of people that clicks on your ad. That's that's essentially what you are showing, right? Now, essentially, like that's one way of formulating it. But in essentially, what it boils down really is that like they're giving you samples. They don't give you like the labels of that sample. They give you like just try to find a concept that will maximize, that will count as much as they can contain like samples from that distribution. You see, and that's called essentially an EMX. Now, the mathematical distribution is this. So.
By the samples, you want to reconstruct the distribution of the overall, like.
No, the distribution you don't know it. Like you are getting samples. Your goal is to learn the concept from which that maximizes the source of your samples. In your case.
What do you mean by learn? Are you looking for zero training error, or are you looking?
That's what I'm going to define. So really, they define something called epsilon delta learner. That's like I'll try to explain that. So because essentially you are approximately learning things. You see, the hope is that the more samples you have, the better your approximation will be, right? So we call that an epsilon.
What exactly?
Sorry.
Approximating what?
Exactly the concept from which you are getting the samples. So you have a concept. Now, by concept, I need you to understand the concept is a subset of X. That was the concept. Like I'm using that concept, that word, in the tradition of this paper. So in this paper, they use the word concept to represent a subset of X, right?
For example, image detection or something like that. The concept is whether this object is detected.
No, the concept is really like, for example, image detection. See, what are we detecting? Humans, for example, right? You see, humans, right? So the concept is really the set of all humans. That's what you're like. You understand?
All humans.
Yeah, the pictures of the humans.
All humans in all of the.
I mean, you're training. So it's for example, if you're working here in Canada, like you assume like the people are living in Canada. Like I'm not looking like at the
So it's still infinite samples.
Yeah, it's an infinite sample. Infinity. Yeah, it could be in theory like X is infinite, and in general the concept is infinite. So you see, like that because concepts really identity. If I'm learning, like let me put this way. Like let me give you a little bit of the background. Maybe hopefully like this understand this. Like. As a human, you see, if I'm learning like the concept of a human, I don't learn that. Like a kid doesn't learn what a human is by studying a definition of a human. So like basically getting samples of what a human is. Yeah, there is some concept, like that after seeing few humans, I'll be able to identify if I see a new object, whether that's a human or a cat. You see, like, so the thing here that the concept you are learning is formalized as a set of items from X. So you have X, the set of things. A concept is a subset of X that represents something meaningful, right? In this case, humans, right? That's what you are trying to learn. How do you learn that? By getting samples from that concept. You see, usually you get positive and negative samples. You get samples from the concept and samples from outside the concept. In this case, what you are getting really is only samples, and you need to find the concept that approximates as much as you can the samples you are getting. So it's in some sense like you don't have the labels here, right? You see, you just give you like samples. You tell me what's the best concept that matches this thing. So if I give you, let's say, like for example, a data set of 999 humans and one cat, what is the best concept for this data set? It's really humans. That's the best concept here. You see, even though it doesn't match all the samples, but that's the thing that approximates as much as you can from this. Yeah.
But isn't your set of measure 0 in the sequences? So can't I always just predict that it's infinite?
Sorry, set of what?
Measure like
P.
No, fx.
Yeah, F. Yeah.
But aren't the finite sequences of measure 0 in the set of all sequences?
Of measure means measures here instead of like probability here.
Yeah.
Yeah, the probability also is finitely supported. So this is why like it's a mathematical technicality, but the probability also is finitely supported. This is why when you measure that, it's not a P on, so it's P on X, but it's a finitely supported P. It's a mathematical technicality. Anyway, so So the idea here that what we really say is that really what we are assuming that we are getting samples. So the question EMX is that I give you sequence samples from X. Give me what is the concept that approximates as much as I can, like the probability from which I'm getting the space from which P is defined. So let me write this and hopefully it'll be mathematical, because the concept here is that I don't want to overfit on my training data, right? See, I'm measuring, like, if you train a model, you evaluate your model by how good in generalizing, not in the training data. It's like I can't always build you like a perfect model, always a star. You can build perfect model, for training data, right? Training data. But the idea really here is that your model should perform well on the unknown, right? You see, as long as
unknown is so it's infinite, so we cannot be sure that whether the
unknown is that
function can be the best.
The unknown is that you don't know what probability distribution you're working with. So this has to respect all possible distributions. So the elements of this F finite, you don't know how they are weighted. In reality.
Can you raise your voice? We can't hear you.
So the unknown is that you don't know what probability distribution you're working with. So in this case, you have infinitely many elements in this finite depth subfinite, and you don't know how these are weighted because you don't have access to the true probability distribution. You're working in darkness, basically.
So the idea is that you have the samples, and then by the samples you want to get the idea of that concept by approximating it.
Exactly.
Then but for example, your true ground is x between 0 and 1 it's like infinite. You cannot get, so since this infinity doesn't have any, this infinite set doesn't have any true distribution to it, you cannot find a learner which can like.
Oh no.
Why is that?
No. Oh, let me put it in this way. You see, so first let me try to explain a bit what do we mean by evaluating, the learner. You see, if I show you a picture of 10 humans, right? You see, now and you guess that these are humans. Let's assume I have some kind of someone from Mars came here, that alien. It's I showed him 10 humans, and he's able to train them. Humans I encountered, he's able now to say no, these are humans. Okay. Now, do you think now this guy can you say with confidence that this guy now knows what a human is? If you have a model that's really able on your training data to have 100% accuracy, can you say that this is a good model? On your training data, if you training data 100 picture, you see, train the model 100 picture, 50% of them are humans, 50% are cat.
If you fix your hypothesis, then you can. You have to because the best you can hope for is the best that so you fix the architecture of your model, let's say, in the more practical language, right?
Let's say I'm using linear model. Let's say
So the best that you're hoping for is the best that's possible given that architecture.
Yeah, but right? The question, this is not a trick question. In reality, you see, let me put in reality, I have a training data. You see,
When listening to that, I would say yes, but right now I'm not sure.
Yeah, no. So let me put it this way: do you evaluate your model on a testing data set, or you just are satisfied with training data? When you train your model, do you use testing data set? I didn't say testing data. Look at the training error. It turns out to be 0. No errors had been committed in training. You see, can you say now, I don't need to look at the testing data because the model is working properly. What do you think? Sorry? Overfitting, right? What do you mean by overfitting here?
It's not generalizable.
Not general, exactly, because the goal essentially.
We don't know if it's generalized.
Yes, so the thing I can say my model is good if it generalizes, to the distribution outside the training data, because the assumption is this: you have a distribution from which you got your training data, right? You trained your model on that data, right? You have 0 training error. You see, your model is perfect. Look at the, it's really very good, unbelievably good. You see, does that mean now I arrived at the perfect model? I can go no, because the real question is really about generalizability of that, right? Now, when we look at the test.
Evaluate this generalizability.
Perfect, very good question. In practice, what we do is that we try to estimate, a theoretical value. Because in real, if you have divine knowledge, Oracle, that can ask any question, you would ask about how would that function, how that model acts in real life, right? That's really your real thing. You don't really care, to be honest with you, about neither training nor testing. The testing data is a proxy for you to evaluate how your model function in real life, right? By saying that, I'll try to mimic the real life situation by showing that model data that never seen before and assess the model on that data, right? That's the essence here. So the testing error is really an approximation, an estimation, to use a more accurate term. It's an estimation of a theoretical error defined by the probability distribution. You see, the probability distribution from which you are getting your samples. So so in theory, like, let me put it this way: if you have, let's say, you know, like, I have a function L. Like, let me just digress a little bit.
Constrained by the sampling error.
The sampling probability.
Sampling distribution.
Yeah, you see, but you don't know that sampling distribution. This is the thing, and the second thing. This is why we
distribution, and also you don't know the sampling distribution. So
what I know really is a sample.
Right.
That's what I know. Right? You see, like, I don't know really, you know, like, the distribution to which my model will be acting with in real life, right? We hope that, you know, like, the sampling distribution, and this is like, you know, a bit like difference. So we have a sampling distribution with which we got the samples, right? We hope that the sampling distribution matches the reality distribution reality, right? You see. But if that doesn't hold, like, if I'm training my model on a subset, on a partition of the space that, you know, has a sampling distribution that doesn't match completely. You see, like, I'm training my model on people living in Canada, and then I'm going to use that, you know, to distinguish, like, let's put it this way. I have a model that distinguishes between males and females in humans, right? I train that, it works well, like, very good testing, you know, like thing, and then I run that on cats. You see, the problem here is that, you know, like, the sampling doesn't match at all, you know, like, the real distribution. So the first assumption is that the sampling distribution matches the real distribution, and under that, even with that assumption, you know, like, the testing error is an estimation of a theoretical error. You see, yeah. And now, why is that? Because that error here I'm defining is really the theoretical error. So usually, how do you define theoretical error? If you have a function, let's say, if you have a model M, you see.
Just as a heads up, you have about 10-15 minutes.
I have 10-15 minutes more. Okay, perfect. So I'll write this and go. So if you have a model M, you see, and you have a function L that when you apply M, let me write it in an easier, in a way. You see, so. So let's say I have a, you know, like, the mx is the output of my model. It's like, it's a classifier, 0 and 1, right? You see, and then I want to, like, whether mx equal y, right? That's the thing here, right? So sometimes this will be 0. You like, if it doesn't equal, this will be 1 if it equals, right? What I would like to do, if it, like, in this classification, but, like, I'd like to, in theory, like, you know, the quantity I'm trying to evaluate is the expectation of that with the unknown probability. I don't have that entity, right, you see, but that's the entity. So usually what we do is that we try to estimate this by having a summation of mxi equal yi over n. Oh, okay. Oh. Okay, so what I try to estimate. So you see what I'm trying, even though it doesn't, I think, work well, even if I zoom, because it's unclear. But I think, like, the idea is to try to estimate this by computing a mean, an average of the errors. That could be like something like the accuracy, right? You see. So that's really here is a practical estimation of a theoretical value. Ideally speaking, I'd like to have that. If I have an oracle that I can ask her or him for knowledge, I'd ask him for that. Be weird question to ask an oracle for that. But anyways, you see, that's the thing here. Because I don't have it, I use it. However, in our definition, when we speak about definition, we speak about it in this way, right? So an epsilon delta, because now the other component to understand the definition is that if you look about that, you know, like, usually you have a training data, right? You see. Now that training data is in irregular statistics, frequent statistics, which is the regular paradigm. Now it's changing, but in the main paradigm, you see, that data is not unique. In any sense, like, there's, like, because if I was getting the data in a different time, get the different data sets, right? It's just a sample from distribution, right? In some sense that, you know, like, this in some sense define a distribution on the models. Because sometimes if I have good training data, I could get good models. If I have bad training, they get bad models. So in other words, there is a kind of a distribution on the models. You see, sometimes you can get two models, sometimes you get bad models, right? So the epsilon delta is really the notion, the two numbers that capture these two aspects. The first aspect is really, you know, like, given certain model, you know, what is the error, the generalization error, the theoretical generalization error, the error that's related to this quantity, you see. The delta, the other thing is that, you know, like, what's the probability of satisfying good model? Because, like, the model itself is probabilistic. So usually if you look at in our context, like you define G, the learner, by a function that takes, sequence from X. I call that X star. X star is a set of all sequences, all training data. It takes one sequence from that and give you like an F, and give you a concept in F, right? Now we say that is epsilon delta EMX learner. EMX is really like estimating the maximum. So some says like giving this data set, what's the best concept that I can give, right? That's what G is, you see. If it satisfies two things. First thing, not something like three satisfies one thing. So if the error computed from G, so let me say that I have a training data or sequence S, right? From that I could compute GS. GS is really the output of G, right? The concept that learned, right? If I compute the probability of that, this is EP, expectation of that, like how good is that model at, like how good is that the concept I learned in capturing P. You see how good the model in capturing P. If that is really smaller than the optimal model, so for each P there is an optimal concept. You see, I'll accept like an error epsilon. You see, so I say that like this is the probability of this error being smaller than this. That means like the higher is the better. You see, so like an ideal concept you're learning is an ideal concept that captures the whole distribution. So in that case, the expectation will be 1, right? If you're giving like a bad model, then like you are really giving under. You see, so the problem of committing an error is smaller than delta, and that probability is based on S. So essentially, like to understand this concept, and this is also good to think about your like training algorithm. You need to understand there are two distributions. The first distribution is the distribution on your model. The model you are getting is a random model. If you're, like depending on the training set, change your training set, you're getting, like a model. That means there is some distribution of the models, right? Yeah.
Sorry. Shouldn't that be a plus, opt plus epsilon? Because the opt is the small. Are you doing loss or?
Yeah, this is errors. You see, yeah. So.
Please repeat the question.
Sorry. So the question here is that, shouldn't this be plus? He was asking like, shouldn't be plus here? You see, I draw minus because. And this is why I say that it's a little bit tricky for this reason. Like, what is GS? Let me answer this.
Because opt is the lowest, the smallest possible loss.
No, but that's not loss. This is not loss. This is the accuracy. Yeah, you see, like,
okay,
yeah, you see. Sure. So this is the opposite. Yeah. Okay. Yeah.
You can formulate in one of two ways.
Yeah. But I use like what the paper used. That's what the paper, like.
So I got distracted for like 3 seconds and I lost track. Could you once more, maybe quickly, just repeat from GX and then rewriting as F, and then the rest?
Yeah.
Thank you.
Yeah. So essentially, G takes a sequence. X star is a sequence of inputs, right? F is a concept. Now, F, if you look at like F, is really a family of sets, right? Each set could be looked either as a set, which is subset from X, or like a set here could be either like a set which is a subset from X, or it could be like an indicator function that takes element from X to give you 0 and 1. Indicator function, like if the element really is from that concept, the function will give you 1. If it's outside, it will give you 0, right? Now, once you have that, then GS is really what concept the model learned out of S. S really is a sequence, right? I give you a sequence, randomly sampled according to some distribution, right? And I try to learn a concept, right? So that's GS, right? Now, if a concept, you look at that as a kind of indicator function. Right? Now, what you try to use the indicator function, evaluate it with P. See how many of the samples this indicator function capture. If that indicator function captured all the samples, then you'd have this will be equal 1 because that's that's the concept that captured all the probability distribution, right? What you want to do, optimal P, you want to if that's like an epsilon delta EMX learner, you want like this to make epsilon error with probability maximum with a probability of delta. You see, so in other words, you want the model to make more than epsilon errors with probability less than delta. So in general, your problem doesn't make errors larger than epsilon. You see, now that concept of epsilon delta is very common in because this is the thing here. You're always estimating a random model that's the source of one error. You see, or one value on a unknown random distribution. You see, like the P here. So you see, the P here is really used for two reasons. The first one is to estimate the error, the theoretical value, and the second is to sample S. So S really here is sampled from P to the D. You assume IID. That's usually that you do your assumption. Yeah. Okay.
If X is fundamentally finite, is the
no, X is not finite.
No, it is.
Sorry?
It was, if X was finite.
Okay.
Would that not fundamentally?
Well, like if it's the problem is that when you have X is finite, then like everything is finite. So then if you can like discuss all the possibilities, you would be able to know whether it's learnable or not, right? So in this case, if I understand correctly, you're saying like if X is finite, will the undecidability hold? If that was your question, the answer is no.
No. Yeah, that's what I'm thinking.
Yeah. So just like it needs to be infinite. You see, you need to have all the yeah. And this is why it's a theoretical. You see, like this construct here is theoretical because the goal is not really to give you, at least at this stage, but it's less theoretical. Okay, like there are.
Because the infinity of the real world is actually not quite.
The infinity
of the real world, real samples, is actually not quite defensible.
Well,
it's always going to be
Yeah. So real samples are really. Let me put it this way: X star is an infinite sequence. It's an infinite set of finite sequences. So you could have the sequences, all the sequences of one sample, all sequences of two samples, all the three samples, like till n, right? Every sequence here is finite. Yet the space of all sequences are infinite. Sure. Okay.
But for example, this infinite set, you cannot have a distribution, right? For example, for real numbers, you cannot have a distribution, right?
You can have a continuous distribution. In this case, you have a density. You define a density. You see, like on this. So, for example, I define like a uniform density, 0, 1. Like, and I'm sampling uniformly any real number between 0, 1. That's possible.
When you're sampling, then you would have a distribution, right? But for the universal set of 0 and 1, you cannot have distribution, right?
What do you mean universal set of 0 and 1?
For example, all of the values possible between 0 and 1.
Okay, that's a real set, right? Like this is the subset of R between 0 and 1.
Right?
Well, actually, you can. Why you cannot? Like
each
that
distribution is finitely supported. Each one of those distributions, the assumption in the setup is that each one of them is finitely supported, right?
Yeah. So speaking about this case, or speaking in general.
In general.
No, in general, you could have like
I mean, the beauty of the setup is that even though the probability distributions that you're looking at are finitely supported, still this goes wrong. So if you want to make it continuous, that's even worse. So this is a minimal example. It's a small example where everything collapses, right? So this is
discuss it after. I think there's a question in that.
Going to the argument that humans are machines, or human brains are machines.
Mind, not brains. That's different. That's different concept. That's different concept. Go ahead.
Sorry. Question. Assume. So we do expect people to know what numbers are, for example, or we do expect people to know how other people look like. Like I just cannot take the concepts that you're saying and generalize it to the case where I feel like I can be confident that Darren or Lindsay would know what a person is. I feel like I can be confident about that. Okay, so how does this framework, like, I feel like I have decided that I am confident that they know what to do, and so how does that work in this framework?
Okay. So I think I'll say it and then maybe like I'll leave it if you want to make a comment. But my thing is like that the result of this paper doesn't say that all learnables are undecidable. That's not what the paper says. It says that there are classes, not concepts. You see, like there are classes that are undecidable. You see, like the class here is in some sense weird. Like it involves infinities and all that stuff, right?
Okay, so there exists some concepts that are undecidable.
Yeah, there are classes that are undecidable. Yeah, you see, like that their learnability is undecidable. If you want to make it,
which means other classes can be.
Yeah, of course, like the majority of the classes, at least those who are working with, but however, the framework, and let me put it this way, the framework. That's one application of it. Try to understand, like the undecidability of because the program here is that like is everything learnable, or there are things that are not learnable, right? And that's the first step. Like there are some kind of a weird situation that's not learnable. Now the program is that how close can we get to real life? You see. Now let me give you a result which might in some sense like resonate with you with this. There is this problem that we know again. Like it's not only there does not exist an algorithm. Whether it's, machine learning, deep learning, any learning, like it doesn't exist. Even if you are thinking as a human to write an algorithm, you cannot do that. And the problem is really, has a practical flavor. The problem is this. I need you to write a function, an algorithm, that will take a Python function, along with its input, you see, and tell me whether that function will go into infinity, will halt, will run forever, or it will halt after some time. Now that problem, of course, like it has a kind of practice. Like if you have some kind of a problem checking, program checking program, you see, if you're writing an algorithm to check whether you are doing bugs, you see, and some type of bugs, if your function goes into infinity, right? That's a kind of a practical thing, right? Just give me like, tell me whether my function will have some input, or my function and this input will stuck or not. That's really the essential of it, right? That problem is undecidable. There does not exist an algorithm, a finite algorithm, that tells you when you give like a function, whether an algorithm in Python, I'm using Python in, like as an example, give me a Python algorithm, give me, like an input to that Python. I know the input, I know the algorithm. Can you tell me, not, like as an, like, can you write an algorithm that will tell me whether that my program will halt or not? That's undecidable. It's known, you see. Now, does that mean that a human cannot do it? Like, does that mean that human cannot do it? You see, now this is an implication. If you think the human mind is a machine, and something like there's some kind of a super, like program, super software networks that like, that really function there, then of course the implication of that holds here. But if you think, like human minds are not machines, and this is why like you see these types of questions about incompleteness, about undecidability. If you read the literature of philosophy of mind, like it's present there strongly. You see, like people, especially those who favor them, like human minds are not machines. They use it like, like extensively. You see, but that's 5 minutes, yeah. But that's like an example of a problem like this.
Yeah, so I've been trying to formulate a clear and succinct way of describing why this paper is really dumb, and so I'm going to try.
Okay.
I want to try it out on you, and you tell me if you think this is accurate. So suppose we come across some phenomenon where there's labels associated with variables of some kind, and we ask ourselves, gee, we seem to be getting lots and lots of test error, and we suspect that the labels are being generated by the variables in a way that is sensitive to the behavior of large cardinals, or non-standard models of arithmetic. Only under those conditions would this paper be of interest to us. And because we know there can't be such a process, because it's totally insane to think there could be, ask any mathematician, then the paper is not even really of theoretical interest. It's kind of a mathematical toy where they've embedded, their model number 2 says, imagine that the closed interval from 0 to 1 is larger than any finite applications of the power set operation to the natural numbers. So it's a non-standard model of arithmetic. So some bizarre weirdness is going on there. And only if the labeling operation were sensitive to that interpretation of arithmetic would we be getting our test error. But that can never happen, so who cares?
So before, like, just try to understand your position here. So what you are saying
in the paper, the most important part for me is where they say, consider 2 models.
Okay.
And the second model is defined by having the closed interval 0 to 1 larger than any finite applications of the power set operation to the natural numbers. And furthermore, we would need to have in nature somewhere the actual generation of labels being sensitive to features of this model. But in general, large cardinals are not constructive. So, it's a frustrating paper for me because it seems it's like a mathematical curiosity, nothing more.
What do you mean by sensitive to?
The labels depend on features of these non-standard models of arithmetic.
In other words, you need to pick a non-standard model of arithmetic in order to generate labels in this way.
Right.
So I'll tell you my opinion on this, because that part specifically, where they're trying to say like there are 2 words. The first word is the model A, where continuum hypothesis, is learned. The other model is this. That part specifically, I disagree with. But to be honest, that part is a kind of a philosophical interpretation about, incompleteness theorem. And the reason for this is this. Let me try to tell you, like, why is that,
I'm just confused why we're mixing the continuum hypothesis and computability.
Okay, let me just try to, like, you're speaking about the case where they say they construct 2 models. The first model in which this is learnable. The second model, this is unlearnable, right? That's what he's trying to say, right? Now, that approach is really coming from how to prove incompleteness. So how do you prove, like, if let's say, like, continuum hypothesis can be deduced from ZFC, you see? ZFC is really a set of axioms. quantitative hypothesis could be a theorem. If you're able to find a model, and a model here really, because if you think about axioms are just statements about a reality. Let me put it this way. You see, about a set, right? So what they do usually is they use kind of forcing, algorithm. They try, in order to validate this, they try to find two realities in which both the axioms and the theorem hold. You see? So in one reality, the axiom of the theorem hold. In the other reality, the axiom and the negation of the theorem hold. And that means, if in this case, then the implication of that, you cannot prove the theorem from the axioms because you don't have inconsistencies, like that. That's, how they mathematically prove. What they are trying to say here is that, but that doesn't tell me that, why this is, for me problematic because mathematics, that FC, is not the philosophy of mathematics means that, sorry, let me try to paraphrase what I'm saying. What I want to say here is this, that way of proving, this theorem doesn't correspond to a mathematical reality. I can't speak that, I'll assume in one way mathematical reality in which, this is learnable, and another reality in which this is non-learnable, right? Because that position really here implies that you are in some sense believing in mathematical multiverse. You see, if you don't believe in that, then you're like, if you believe that in reality, for example, this gentleman was saying that, no, there is in reality one correct, there's one correct answer. The fact that my axioms are, limited doesn't mean I can't prove the correct answer from these axioms. That's another way of looking at the theory. So that part specifically is really, I think, the weakest part, in the paper. So I agree with you that there is some sense of frustration here. You see, I could see this. However, for me, that paper was a kind of the interest of that paper is really to just so again, this is what this is the first step. If that was the last step, then I agree with you. So I agree with you in the sense that this is a toy problem. You see, I agree with you. It's not related in any sense to any practical thing, that we have. I disagree with I agree with you, and I disagree with the way that they interpreted their things, of assuming this kind of a mathematical multiverse. So I agree that piece, is the weakest. But I still think that as a research program, now this is the first step. Can we start getting closer to instances that are, more interesting about the concept of learnability in general? You see, so this is how I interpret this paper. You see.
So we are out of time. Okay. I'm curious to hear your verdict, and then we close on that. Yeah. Just a few minutes.
I want to say, a parallel to your concern is, I kind of see where you're coming from, but it's like turning the clock back 200 years and saying that, who cares over complex numbers? Every matrix has an eigenvalue because complex numbers are 0 or no. We don't know if we're going to run into a situation where having the non-standard setup is useful or no. At this point, it's a toy. We're playing with it. Yeah. But the complex number I, can you justify the existence of? Now we're comfortable with it. But that's the only thing I can say. But I see where you're coming from. That makes sense.
Okay, so let's thank Abdul for making such a fascinating discussion. Also, AJ, wherever he is, hosting in Statistical.